Okay, everyone, let us get going because today we're going to do some math. And I know how excited you are about that, so I do want to make sure that we leave ourselves enough time to go through it step by step. So today we're going to talk about how we actually go about measuring glacial ice mass balance, because we talked about all of these different things that go into creating it, but actually how do we go about measuring that? And so we're also then going to move on to really thinking about ice dynamics. So in other words, how ice moves. And that's really going to occupy us for the rest of today, but also next week as well, because it's a really important part of understanding glaciers. So first of all, quiz 6 is going to be available. I have been in a really long meeting at lunchtime, and so please could you give me until 4 p.m. today to start it. But Monday is a holiday, and so I'm giving you until Wednesday to complete the quiz, okay? So it has to be done by 2 p.m. Wednesday. So a couple of other little announcements. There are no discussions on Monday because it is a holiday, but if there are any students in Monday discussion groups, you are welcome to go to any other discussion next week, because I don't want you guys to miss out on doing the activity if you would choose to do that, or just sort of having the chance to ask a few questions. I've had to unfortunately cancel my Friday office hours. I'm really sorry about that, but I still do have office hours on Monday, Wednesday, Thursday, and I haven't been getting huge numbers of people, so hopefully I can still accommodate everyone who would like to see me. And if you can't make the times that are listed on the class website, please do email me and I'm happy to make an appointment with you. Okay, so midterm, don't panic, it's not next week. The following week, but I wanted to give you enough warning that there will be a midterm review session at 3 p.m. next Friday, so a week today, immediately after class. And this time we've actually managed to book this room, so you don't have to go anywhere, you just need to stick around, and you can ask the TAs questions related to the quizzes, anything on lectures. If you want to go through anything from discussions again, things like the trumpet diagrams, that would be a really good chance to do that. Does anyone have questions for me about any of that stuff? No? Good. In that case, let us think back to Wednesday. It feels a very long time ago somehow. And we got to this point where we said that we're basically doing a bit of sort of integration or calculus. So that change in volume over 1 year is basically equal to the amount of accumulation we see. So how much snowfall, how much avalanching, how much is added to the glacier or ice sheet, minus the amount of surface melting, the amount of basal melting, if we're ending in water, the amount of calving that would happen, and also sublimation as well. Okay? And we said that if we're going to do this accurately, we really need to talk about water equivalent, because again, if we talk about snowfall and the sort of thickness of snow, that's going to be a really different weight and sort of mass of water compared to, say, if we lose the same thickness of ice. And so whenever we talk about glacial mass balance, we always talk about water equivalent for the same reasons that we did this when we talked about snow. So here's a question for you. That's our little equation that tells us how our glacier is changing. How easy do you think it actually is to measure this? People at the front are shaking their head. It's not going to be easy actually to get at all of these components. And so what we're going to do is think about how we might do that. Okay. So just to remind you, this is a relatively small little glacier, and they've studied this one quite well. And so they're able to point out things like the equilibrium line just because we can look at it. But if we want to get into more detail about actually how much mass is added in that accumulation area, how much is being lost in ablation area, we actually need to go and study these things much, much more carefully. So first of all, how would you measure accumulation? If I told you you had to go off for 6 months, okay, and tell me at the end of that 6 months how much snow that was accumulated, what would you do? Giving up isn't an option. I'm too mean about that. No? Okay, well, I'll give you this one, and then maybe you can tell me for ablation what you would do. So first of all, one of the easiest ways is if we just go and put stakes out. So before the winter, we go and put a stake out, and we sort of mark off different depths, then over winter as that snow falls, then we'll be able to see the difference from when winter began and when winter ended. Okay, so if we just put big stakes across our glacier, we would be able to get an amount of snow. Okay, but we do need to make enough measurements that we could do that all across the glacier, and that would be somewhat difficult. Okay. Also, do you remember our snow is different densities, so just because we have the thickness again doesn't necessarily mean we have the actual mass of snow that's added. And so what you can do, and what you have to have lots of students to do, is dig holes, okay? And this isn't easy, and so this is not something that you do terribly often in very many places. And let's just experience quite how challenging that is, okay? So we'll let them carry on for a while. And so what they're doing by digging this is they're trying to find the depth at which, so the last sort of summer, or the depth of snow that fell that winter, okay? And by doing this, by digging a hole down, you can actually sort of identify the horizon where that happens. And this is especially true in glaciers where we see lots and lots of snow. You can't necessarily stick out enormously tall stakes to do this. And so what we can also do if we dig a hole is we can get an assessment of the density of that snow at different depths as we keep going, okay? So they lose more and more clothes as they keep going because this is really hard work. So it may be cold, but they're still going. So if you ever get asked to go and volunteer to measure the mass balance of a glacier, now you know exactly what you're in for, okay? And so then this little dude tells us sort of about that. So you can watch that in your own time, but basically what they'll do now is they've found, you see that little blue line running through the bottom of the picture there? That's really that sort of last sort of summer melting from the last season, and then all of that snow that they dug through was actually just from that winter. Isn't that crazy? And so what they then do is every 10 centimeters or so, they'll take a sample of the snow and they'll weigh it, and so they get a sense of the density as well. Okay, so this is obviously not something that you can do repeatedly all across the glacier. Okay. So it's not terribly practical, but we do get really good data that way that we can use to sort of interpolate for the rest of it. Okay. So let's think about how we would measure ablation. Okay, the snowfall in some ways is a little bit easier because at least something is falling from the sky. With ablation, we can do the same thing but in reverse. If we go at the end of winter and stick a big sort of long stake into the ice, if we then go back at the end of the summer, it'll end up sticking out above the ice because the ice sort of where it used to be has melted away and it's left that thickness behind. And so what we can then do is measure the height that has changed again. Okay? And so again, if we do that in a network across the glacier, we can get a sense. And this is something that's much more likely to change across our glacier. But again, it's time consuming and it's hard work. And I wanted to show you, there's a really cool little video made by the National Park Service of Mount Rainier and the national park up there. And this is sort of what they spend, or a couple of people spend their summers and winters doing. And so it shows you a little bit of the challenge.
I have to admit, when I'm out on the glacier and we're carrying all the gear and we're at high elevation and you're working really hard, I definitely ask myself whether I really want to be doing this. But you look at the scenery, and there's really no other place that I would rather be at that moment.
Logistical issues with monitoring these glaciers are about the toughest part of this. Getting to them safely and back safely requires an awful lot of work, and so we depend on having staff at Mount Rainier and our Cascades. There are several reasons we monitor these glaciers. They're habitat for certain species, and they're part of the alpine food web. They're a tremendous indicator of climate change. But probably the most important reason we monitor them is because of the water. And these glaciers provide a substantial amount of water during the summer that fuels the hydroelectric industry in the North Cascades. The glaciers are also providing a considerable amount of meltwater to our rivers and lakes, and so they provide what we call buffering capacity. In the summer, when we get very little rain, these glaciers continue to provide water and buffer our lakes and streams from the summer drought or droughts over longer periods. So we're connected to the lake and the aquatic monitoring, as well as providing this overall weather and climate information.
So in the spring when we come out and we are placing the ablation stakes, we rely on the steam drill, which the inside is basically like a camping stove. We have a propane tank, we fill it with water, we heat up the water, and it produces steam. You know, the pressure builds inside, we release the pressure, and then we have a 13-meter hose that the steam comes out of that we drill directly into the glacier. We drill 13 meters and we place the ablation stake down in the glacier, and then we can come back and watch it melt off that stake.
So they continue on for a while, so hopefully that's inspired you to watch a little bit of the rest of that. But you can see some of the challenges of doing this is that you have to sort of get this equipment up and down and sort of measure these big changes all across the landscape. But it's very important that we do that. So if we have our ablation stakes, that's all very well. But what are our ablation stakes actually measuring? Those ones that we stick into the surface of the glacier. Is it sublimation only, the surface melting and sublimation? Surface melting only? Do we include basal melting in there, or basal melting and carving? What are we actually measuring by using those ablation stakes, do you think? So consult your neighbor, see what they think too. Do you have any more votes? Right, let's take a look, see what people think. So 47% of people think it's surface melting and sublimation. And I would argue that they are right. Okay. Because, remember, sublimation is happening from the surface, as is surface melting. What's the problem with, why can't we necessarily get it basal melting from these stakes? My TAs are answering for me now, absolutely. So it's because those stakes are anchored in the ice, right? So if the base is melting, both the glacier and the stake are going to sink at the same amount. And so we're not going to see a change between sort of the amount that's sticking out the top if everything is just dropping. So to monitor things like basal melting, what we tend to do is monitor the amount of water perhaps coming off, and we can sort of do a little calculation, work out what must be surface melting, what must be basal melting. And carving is obviously something that's really, really difficult to get at for some of these areas because there we're having sort of melting below water as well as above. So it gets really quite challenging. So this is a hard thing to measure. It's all very well saying, oh, it's really simple, we just have to know this and this and this. It's actually very difficult in the real world to do this and very expensive. Okay? So we have tried to find other ways of doing things. Because we do have these amazing satellites now, we also can use planes in some of these cases as well. So some of the ways that we've tried to do this are by looking at the change of elevation. So we have satellites that come across and they beam down radio waves or lasers at the surface, and then they receive sort of the bounce back. And if they time how long it takes to go down to the Earth and back again, they can get a sense of how far above the Earth's surface they are. So if they come back the following year and they do the same thing, then they might be able to see if there's been a change in the surface elevation. Okay? We can also look at things like the amount of gravity. So we talked about Grace in the second lecture, I think it might have been, and we said that if we're looking at really large bodies of ice like Greenland or Antarctica, then the amount of water that's being added and taken away from those really ginormous ice sheets actually changes the amount of gravity that a little satellite flying above will feel, okay, which is really astounding. And then we can estimate how much sort of mass is being added and taken away by working out how much movement we're seeing. Because if you're adding mass in one area and losing it in another, then if you're sort of seeing flow of that glacier, then that gives you some idea, perhaps, of what is happening with the mass balance. Okay. So what are the challenges, though? Why aren't we just measuring all of our glaciers this way? Well, first of all, if you have a really small glacier, like some of the ones that are left in the US, they're getting quite small now. It's very, very difficult to do sort of observations with satellites. So we get a poor spatial scale, and we also can't measure really, really tiny changes. And we also can't get at things like density necessarily if we're just looking at changes in the height. They also don't tend to work terribly well in really steep slopes, which is a problem because where do we find most of our glaciers? Up in the mountains. And that's because if you imagine you're bouncing down a sort of laser beam or something to the Earth's surface, if it hits a really steep slope, it's not going to bounce back up to you, it's going to bounce somewhere else. Okay, so it's a really challenging environment for measuring these things. So we just have a certain amount of limited accuracy, and we also can't really go that far back either because these satellites haven't been around for a while. So what do? Okay, we sort of do our best with what we have. And this is a very depressing graph showing you the change that we're seeing in different parts of the world. So this is why knowing your geography is a good idea. So the blue line is Europe, the purple line is the Andes, the orangey line there is the Arctic, black line is the Asian high mountains, so Himalayan areas, and then the green are the US, sort of Alaska and the Northwest. And then that red there is Patagonia, which is at the base of Argentina, right at the bottom of South America there. And you can see that if we go from 1960 to sort of 2000 and beyond, we are losing ice. There was a little brief period when Europe was actually growing, probably because of an extra moisture supply. But really, it's pretty clear that for the last sort of couple of decades, our glaciers have been shrinking everywhere. Okay, and by quite a lot. Okay, that sort of mass balance is sort of a very, very large number. It's 10 to the 3. So we are concerned about our ice and our glaciers, and so we would like to be able to monitor them. And one of the easiest ways of actually doing that is by looking at the position of the front of the glacier. Okay. So if we can't sort of send teams of people out for the summer to measure all sort of the thousands of glaciers around the world, and our satellites aren't always that good, then what we can do is sort of use an estimate instead. And so what we can say that if our mass balance is positive, if our ice sort of mass is growing, then what tends to happen is that the front of that ice, where that glacier ends, tends to move down the mountain a bit. It moves further away. Okay? If our mass balance is negative, if we're overall losing ice, then the end of that glacier tends to retreat up the mountain. And if there's imbalance, then there should be no change. Okay? So what we can then do much more easily by looking at old photographs or looking at even like postcards from the Alps, some people use, is get a sense for how things have been changing through time without having to go out and dig very big holes. So this is what we get if we look at all of the glaciers around the world. And this is a relatively complicated diagram, so I'll explain it first. So each of these little different bars going along shows a different region. And down here at the bottom, this is sort of what happens worldwide. The number, that height of that bar there, is sort of how many glaciers were counted. So you can see that really back sort of early on in the 1800s or so, then we just weren't really interested in measuring them. We don't really have records for them, so we don't necessarily know how they were changing. But as we go forward in time, then we're actually pretty good at monitoring quite a lot of the glaciers around the world now, at least seeing whether they're advancing or retreating. So in red are the ones that are retreating, and in blue are the ones that are advancing. Okay? And you can see that one of the really interesting things is that you see in Central Asia, we suddenly just stop measuring things, and that's to do with the fall of the USSR and things like that. So it's an interesting thing to do, but it's expensive, and that's why we have only a few measurements. And so tell me, what is true? Recently, all glaciers have been retreating. Recently, most glaciers are retreating, but some are advancing. Or there's no change through time in how many glaciers are advancing or retreating. So what of those is true about my diagram on the right-hand side here? Any more votes? Thought so. Okay, let's take a look. So yes, so most glaciers are retreating. So if we look at the bottom column just here, then that red there, that shows how many glaciers are retreating. But there are a handful, a very small number, just right down at the bottom here, that are blue, that are advancing. Okay, so all of this number are retreating, but this handful down here are advancing. And you can see that at certain decades in the past, so around the 60s or 70s, you can see that many more of the world's glaciers were advancing. It was particularly cold because of various climate sort of oscillations. And so it was relatively cold in the 60s and 70s, and so we grew a few more. But really since then, we've seen a steady decline in that. So the question is, why are there such different responses? And it comes back to this idea again that these aren't necessarily simple systems. So if we increase temperature, that's not going to make a huge difference to some of our really cold polar glaciers. Remember, those ones that are beneath freezing all throughout the year, all the way down to the base. It might make a tiny difference, but it's not going to make a really substantial difference. Where increased temperatures will make a huge difference are in those more temperate glaciers, those mountain glaciers, which do have a lot of meltwater going on in the summer. Okay? So definitely increased melting of those will have increased runoff. Also, we're going to melt and refreeze that snow more frequently. And also the fact that we have more water at the surface to seep down to the bed means that they're going to be moving faster as well. So they also start to thin out a certain amount because more of that mass can be transported to lower altitudes where it can melt. But then if we're going to have higher world temperatures, we already talked about this when we talked about snowfall, we might get more precipitation in some places. The question is, will that precipitation fall as rain or as snow? Does it make a really significant difference? Probably not if you're at the coast, maybe so if you're a long way inland. And so there's a real sort of complication to where your glacier is to how it's going to respond again to precipitation. And then there are little feedback mechanisms that kick in. Things like if we're melting more, we're going to have a lower albedo because that lovely white, perfect snow surface. We saw it looks a bit crappy once it sort of melted away and we just get that ice surface underneath. So if we're melting more of that ice due to that snow during higher temperatures, then that exposes more of that old ice and that then melts away more easily because it has a lower albedo. Okay? And so all of these feedback mechanisms really complicate our response. And so yes, the vast majority of glaciers are retreating, but of course there's going to be a couple where these factors sort of coincide that means that they grow a little bit. Okay? So it's a quite complicated system. But no matter where we look, we can see that as we get warmer and warmer and warmer, we are going to be losing glacial ice. And that's really of most concern around places like the Andes and the Himalayas, where so much of the water from those mountains goes to people, to agriculture, to industry. And so this is sort of how much of our glacier we might have left if we go to sort of really high. These sort of numbers don't mean a lot to you, but so the yellow is obviously less emissions, red is higher emissions. And you can see that in those higher emissions, we're losing amazing amounts of our mountain ice potentially by the end of the century. So we're going to come back in week 8 to think about what might happen to things like the stream flow throughout the year and whether that might lead to floods or droughts. So more about that in week 8. So, but because now we're going to really move on to talking about dynamics, because we sort of talked about that already when we talked about advancing and retreating. Because really what we're thinking about there is that mass is being added at the top, and it has to somehow get down to the base. And so if we're adding less mass at the top, then we're not going to be able to move it as far down. Okay, so really we've already introduced this idea of dynamics. And that's our sort of definition of a glacier. It's a solid body of ice, and it has to move under its own weight due to gravity. So a glacier has its area of net accumulation, which tends to be at the top, where we get more snow and colder temperatures, and an area of net ablation, which tends to be lower down, where we have warmer temperatures, perhaps more rainfall. Okay? And we have a mass budget which balances those out. But what we haven't really thought about yet is that dynamics, that movement from that accumulation zone to our ablation zone. Okay, it balances out. So let's think a little bit about how ice moves. So first of all, why does the ice move? Because it's heavy. Okay, if you're going to pile lots of stuff up, it's going to sort of flow. And that's because this ice is sort of flowing. It's not necessarily moving as a solid. So here is time for some maths. Is everyone ready? Everyone excited? No? Okay. So I've given you a very, very simple case here. And we're going to walk through it step by step, so you will all get this, I hope. So first of all, we have our sort of nice blue glacier. It's the same thickness along that slope at least. Okay? And the angle of the slope of the ice, as well as the sort of slope it's sitting on, is alpha. Okay? Really, actually, the most important thing is that that is the same angle as the ice. The ice surface is what drives that. But for purposes that I'll show you later, I've put it there. Okay? So alpha is that slope of the ice. And that alpha is actually measured in radians, not degrees. Do you vaguely remember hearing this at school a very long time ago? Radians? Okay, this is radians. It looks like a horrible mess. Don't panic. I can hear it from here. Don't panic. Ready? Shh. Okay. So over here, start on the right-hand side with me. Over here we have 0 degrees or 360 degrees. And what that is equal to is 2 times pi, just like the pi you have on your calculator, 3.14. If I move around to 30 degrees, at 30 degrees I'm 1 pi, so 3.14 divided by 6. At 60 degrees, I'm 2 pi over 6, which is pi over 3. Okay, at 90 degrees, 3 pi over 6. So it looks a disaster. It's actually following a very logical sequence. Okay, so don't panic. Look at the numbers, and it makes sense. Okay, so according to that sort of circle, look at the sort of the right point. What would 30 degrees be in radians? Okay, have we got everyone's votes? Right, let's take a look and see how we did. Good, 95% are with me so far. That's a good sign. Okay, so you're right. If we look at where 30 degrees is, it's basically 1 pi divided by 6. That's all you'd have to do. Okay? So, let's go back to our diagram. So why is my ice moving? Because it's heavy. There's weight. Can anyone remember from school what the formula for weight is? mg, mass times gravity, absolutely. And what is the mass? How would we work out the mass of our ice? How do you measure the mass of your ice? Density, yeah, absolutely. It's the thickness and the density. Okay, so you guys are doing well. So here's my weight, and it's acting straight down. Okay, it's acting straight down with gravity. Okay, and so that's equal to mass times gravity, and my mass, which we can't sort of go and measure necessarily, but it's related to the thickness, which is my h. See my h on there shows the thickness of that ice, times the density times gravity. Okay? Is everyone fine about this part of it? Yes? Okay. So that's all very well, and that's what's pulling it straight down. But we're not necessarily interested in the force that's going straight down. We want to know what's going sideways, don't we? Okay, because that's what's going to get our glacier to move. So what we're actually interested in is that part of it. And we call this the driving stress. And that's what we're interested in terms of sort of how and whether our glacier is actually going to move or not. Okay? And I've done something a bit misleading, which is I've drawn it at the top there. If we're thinking about the mass of the ice, where is actually my force acting? Is it acting at the top or at the base? It's actually acting at the base. For geometry reasons, I've put it up there, but actually, because we're thinking about the full height, we could do a calculation near the top, but we'd only use a tiny bit of the height. If we're going to use the full height, we're really thinking about that driving stress at the base. Does that make sense? Yeah? Okay. So, how would we go about calculating that driving stress? How do we go about? Well, it's a bit like a triangle, right? And everyone knows how to get at this sort of problem. But what we need to know is what that angle is. We need to know that angle between our vertical sort of weight pulling it down and actually that sort of perpendicular to the slope. Okay? So we need to know what that angle is. So this is why I drew my alpha here, because we're going to do a little bit of thinking. Okay. So if I redraw my surface, okay, it's still at the same slope. If we redraw that surface further up, okay, then you can see that there's 90 degrees between the horizontal and the weight coming down, okay? And so the angle of my slope is alpha. So what would be the angle between my weight and that slope? So what would this angle be? How would you calculate that? Yeah, it's 90 minus alpha, okay? So let me redraw it in another way. What happens if I draw it that way round now? Okay. What is my angle here? What's my angle between this weight and this surface? 90 minus alpha. So what must this be to make it 90? Alpha. I feel like I've lost people. Do you want me to do that again? Yes? Okay. So, we have our nice flat surface with a slope. And what we can basically do is just sort of pretend that our horizontal surface is just a bit further up. And so we can redraw it. Oh, other way. There, okay? And there's now 90 degrees between my sort of imaginary horizontal surface and the weight moving down, okay? So the angle between my horizontal surface and the slope of the ice is alpha, okay? And if this is a 90-degree angle, then this means that this angle here has to be 90 minus alpha. Is everyone with me that far? Yeah? Okay. So now what we can do is we know that this angle here is 90 minus alpha, and we know that this is a right angle, okay? So if this is 90 minus alpha, and we have to make it up to 90, then this therefore has to be alpha. So this is 90 minus alpha plus alpha equals 90, which is equal to our 90 degrees, okay? So a lot of steps in there, but if you're sort of finding it challenging, draw it out yourself this weekend and see if you can work out why that's the case, okay? So what we have now is something we can solve, right? What are we going to use? Soa Katoa, absolutely. You remember this from school? Ah, yes. Look, there's a real-world application for this, okay? And so you can see that. Which one am I going to use in this case? Am I going to use sine, cos, or tan? Hang on, I got 3 different answers there. Think about it for a sec. Think about which is the opposite, which is the adjacent, and which is the hypotenuse. Okay, so let me ask again. Which one am I going to use, sine, cos, or tan? Sine, thank you. Okay, because I have x, which is opposite my angle, so that's the opposite. And then I have the hypotenuse, which is my weight, my h density and gravity, okay? So I have opposite and hypotenuse, so I'm going to use sine. So sine of alpha is equal to x divided by that, the thickness times the density times the gravity. Okay? So then all we need to do to find x is rearrange that equation. Okay? So now I've just rearranged that equation so that my x there is sine of alpha times by the height times the density by gravity. So what looks like horrible maths really isn't that bad. It just needs to bring together a few things that you haven't done in a very long time. Okay? And that's our driving stress. That's the force that is trying to move our glacier down the slope. Okay? And so that's a really important thing. And so let's think for a second about actually how ice deforms. Okay? So ice is what we call a viscoplastic material, which is something a little bit weird. Okay? And it's plastic because if we put enough pressure on it, it will flow. Can anyone think of something that they may have had when they were very young that acts that way? Do you remember having plasticine when you were a kid? Play-Doh. Oh, sorry. Plasticine, Play-Doh. Same thing. This is actually called blue tack. We use it to stick posters to walls in England. And so what happens is that right now it's just a lump, right? I would hope that no one would argue with me that this is a solid. But it can flow. If I put enough pressure on it, it's really cold and so it's not flowing well, which is also something that ice does. And so you can see that if I put enough pressure on it, it will flow. Okay? And ice behaves in a very similar way. And people do experiments using this as an analog for ice, and you can get sort of beautiful glaciers flowing down your table with this stuff. Okay? So if you put enough pressure on it, it will flow. But if you put too much pressure on it, it will break, it will snap. Okay? So if I pull that really hard, it's not going to work right now because I can't get it to move. But if I pulled it really hard, it would actually snap. There's a point where if you just pull it really abruptly, it will snap. Okay? And so what we have is once it gets going, it really does behave like a fluid. It's really beautiful. But we have to put a lot of stress on it for it to do that. And we have two particular types of ways that ice can move due to this driving stress. We have basal sliding and internal deformation. And basal sliding is just what it sounds like. It's basically the process where the whole thickness of our ice will slide on a thin layer of water underneath. Okay? Can anyone think of an example where this is helpful in your summer holidays? Summer holidays. You got it? Yeah? Would you do this if there was no water on it? No, it's really not a good idea, okay? And that's because we need that sort of slide, that friction to be less, okay? Otherwise it hurts a lot, okay? And so this is really the most important where we have that water underneath the ice. It makes the glacier behave a bit like a slip and slide, okay? And so it definitely won't occur where our base is frozen. And if you've ever wondered what this would look like underneath the ice, there's a really fun little video. I think it's done on the same glacier, oops, wrong thing, that the time-lapse was that I showed you the other day. You can see how much water is underneath that glacier there. So this is from a tunnel that they had built. And so you can see if we run a time-lapse, the ice is on the top there. Look, you can see it just sliding down, okay? And it's because there's enough liquid underneath that base that the whole thing just slides. And that's really fun, okay? So that's what basal sliding is. It's just the whole movement of that ice there. And we'll come back to this video a little later in the course. Okay. But what happens then where our ice is frozen to the base, where we don't have this water underneath? Our glaciers still flow in Antarctica and everything else. They don't just sit there. So how do they move? Okay. So first of all, let's think about basal sliding a bit more carefully. So we just did our calculation to work out the driving stress. In order to actually get my glacier to slide, that driving stress has to be bigger than the friction, or what we call the basal drag that the glacier experiences, okay? It's the reason that if I put this here and I push it a little bit, it will stop moving, okay? I have to push it with a certain force in order to get it to move, to overcome the friction of the table. And that's true in the real world with glaciers as well. Yes, there's this driving stress, but it has to be bigger enough that it overcomes the friction with the bed for it to do that, okay? So what sort of things do you think might affect the basal drag, how much friction the glacier experiences? Well, first of all, whether there's water or not, that's an obvious one. What else might affect it? If I have to push this along the table, will it be easier or harder than along the carpet? So actually what is underneath the glacier might make a difference, right? Whether it's hard, solid rock, or whether it's soft sediment, that might make a difference to how much basal drag we experience. Yes? Okay, so it'll slide pretty nicely across solid rock. What might happen if the sediment is really, really soft? Yeah, absolutely. So it might do a couple of things. It might mean that the glacier can slide less well, but also it might mean that the sediment itself actually moves rather than the glacier. So it just sort of gets carried along. Okay. The other thing that might affect it is what happens if I tried to push my eye clicker up there? Am I going to get very far? Why? There's stuff in the way. So whether there's stuff in the way might also affect our friction. So how even that surface is, whether it's a beautifully polished surface or whether actually there's things that, like obstacles that it would have to travel along. So basal drag will depend on the temperature because of the presence of water or not, the softness, so whether it's solid rock, whether it's sediment, and the roughness, so basically how uneven that base is. Does that make sense? Yeah, we'll talk more about this next week. So let's come back to our polar glaciers where there really isn't very much water around. So how on earth did these things move? Because they clearly still do. Well, in this case, we have what we call internal deformation. And this is what happens. It means that if we get enough sort of pressure on our ice, enough sort of driving stress, then all of those randomly orientated crystals start to align themselves. And then they'll actually start to slide past each other. So those individual crystals of ice, which deep down can get pretty big, will start to slide past each other just like a deck of cards. Okay? So when you put pressure on a deck of cards, often it will slide out to the side. And so if we're putting pressure on this side, then we're going to get our ice sliding along like that. Why is the bottom one not sliding as far as maybe the top one? Friction. Friction again, okay? It's going to be more difficult for it to slide. Whereas the one at the top, it's feeling the cumulative movement of all of the ones underneath as well, right? So it's easier for it to move further. More about that next week as well. Okay. I should have taken that one out, sorry. So, when will this happen? This will happen when our driving stress is greater than the strength of that ice. So really this is happening all the time. It's even happening in our temperate, our nice sort of warmer glaciers. But it's so slow that it's really nothing compared to what's happening in terms of the basal sliding, okay? And so really this is most important for those cold glaciers, and it is much, much slower than the basal sliding. And so things that affect the strength of the ice might be the temperature. I just said, right, if you have your Play-Doh, if you want to get it to move, you will have to warm it up for a while first. So things like the temperature of the ice, whether there are impurities in the ice, whether there's lots of sort of dust or rubble in there as well. And also things like the crystal size will affect how easy it is to slide those things past each other. Okay? So those are some of the things that affect our internal deformation. Okay? And let's see what I have. That's all I have.